All right, let's put everything together that we've learned about combinational logic to take a sort of quasi real world pro problem that's presented to us as a word problem and solve it and actually design a circuit that can implement the logic that we need. This is problem 222 from Digital Logic Circuit Analysis and Design. If you want to follow along, but I'll also explain it right here. So we have a burglar alarm designed so that it senses 4 input signal lines. We have a function that has 4 variables. The first variable is A, and that is a secret switch that is closed, and that equals a logic of 1. We have a pressure sensor that lets us know if the safe is in position, so unmoved, and that equals 1 as long as the safe is unmoved. We have C, which is a clock, and the clock, as long as the time is between 10 and 2 normal bank hours, then the clock is set to 1. And finally, we have D, which is a closet door being closed or open. And if the closet door is closed, then our logic is set to 1. We want the alarm to equal 1, which is when it actually buzzes, if, and now we have some logic that says when the safe is moved and the control switch is closed, or when the closet is opened after banking hours, or when the closet is opened with the control switch opened. So we'll just keep in mind that we have key words here. We have and or. When the safe is moved and the control switch is closed. When the safe is moved, B is 0, so that would be B naught, and that is ANDed with the control switch being closed. Control switch is closed, that would be A. It's just set to 1, so we have A, not B. Or, so we put a plus here, or when the closet is opened after banking hours. So when the closet is when the closet is opened and it's not banking hours. So that would be closet open, that would be not D, and it's not banking hours. So that would be when this statement is not true. So that would be not C, not D. And then finally it says or when the closet is opened, so that would be not A, and the control switch, oops, got that wrong. When the closet is opened, that would be not D, and the control switch is opened, so that would be not A. Okay, so that is our sum of products. And now we're going to take the question one step further, and we're going to try and design a circuit that will actually solve this problem. So let's plug this into a K-map. 0, 0, 0, 1, 1, 1, 1, 0. Okay, let's look at A, not B first. That would be 1, 0. When we have a 1 and a 0, it doesn't matter what C and D are. They could be anything. So all of these would get a 1. When we have not C and not D, that would be not C and not D. Both of them are set to 0. that point, we don't care what the A values are. Any A and B situation works. So we get 1s here. And then finally, we get not A, not D. Well, this is not A right here. We have A at 0 and A at 0. And let's look at where we have not D. We have not D here. Well, we already have some 1s there, so we're set. And we have not D down here, so we need to put some 1s here. Okay? And if you were unsure as to whether you got the K-map right, well, then don't look at the answer, just look at the K-map and try and minimize it. If you minimize that, you'll find that you actually get this equation right here, which further lets us know that this is a minimized form of the sum of products for this equation. Okay, now we're going to implement this circuit, this logic function, on a 74153 IC chip, which is it's two 4-to-1 multiplexers that both have the same input. So there are a couple of different ways to create this this using 4-to-1 multiplexers. But because we're using the 153, we're a little bit limited because both inputs have to be the same. Okay, so I'm going to use A and B as my inputs for both of these multiplexers. And I'm doing that because this K-map is set up like that. And the way we'll approach this problem is we'll split up our multiplexer so that the first multiplexer is dealing with the C variable in our equation, and the second multiplexer deals with the D. So this one will handle C, and this one will handle D. And then we'll figure out how to put this all together to tell the alarm to go off at the end. Okay, so first, when A and B are 0, 0, what values can C take on? Well, for this to be true, we have here and here C is equal to 0, and down here C is equal to 1. So it doesn't matter. C works for either one of those, so we'll put a 1 there. Then we come to 0, 1, and it looks the exact same way. C could either be 0 or 1, so we'll put a 1 there. Then we'll look at 1, 0. Here, oops, that's right here, right? Again, C could be 0 or it could be 1. It could be 0, it could be 1. So we'll put a 1 here as well. And then for 1, 1, we can only have not C. So we'll put in not C here. For the D, when A and B are 0, 0, D can be 0 right here, or D can be 0 down here. So that would be not D. For 0, 1, it's the same thing, not D. For 1, 0, it can be anything, right? So we have to put a 1 there. And for 1, 1, it's not D. So these multiplexers on their own don't output the correct logic, but of course they both have two outputs. We are looking for situations in which both multiplexers are outputting true statements. That means we use an AND gate. Okay, and let's just test two random spots. Let's pick this spot and test it out. this should not, this should give us a false statement. This should not output a 1 out here. So we'll look at C first. A and B are 0, 1, so we're dealing with this line of logic here. And when A and B are 0, 1, C is 1. Well, this is a 1, so it just always works. So this outputs a 1. So then we come and we look at D. Well, D is 1. We come over here, and this is not D. So this is 0. So this outputs a 0. Remember, both statements have to be true for an AND gate, so this outputs a 0. Okay, let's look at one of the true statements and see if it pans out. We'll look at this one here. So 0, 0. So we're looking at these two selections. When A and B are 0, C is 1. So it should be C. Well, C is just 1 already, so this is already true. And when A and B are 0, 0, D is 0. But this is not D, so it would be a 1. So this becomes true, and this becomes a 1, and this outputs a 1. So you could go through and look at the whole K-map, but you'll find that this actually does work for every one of these boxes. Okay, so in summation, we took a real-life problem, wrote it down into terms, created a minimized logical equation, plotted that equation onto a K-map, then used the K-map to design a circuit using a real 74 153 IC chip.